Hello, everybody, and welcome to the Transmission Podcast. It's me, Quentin Scrimshire, and this week we've got Dr. Neil Kidner, co-founder and chief scientific officer at Adena Power. Now, we're going to talk about a topic we haven't done on the podcast before, and it's a very hot topic right now in the battery world. It's sodium-ion batteries. So if you're involved in the lithium-ion space and you're curious about sodium-ion, this is a podcast for you. And if you like it, please hit like, subscribe, and stick a comment in the comments. It really does help us increase the reach and get to more listeners. So without further ado, let's jump in. Neil, thanks for joining us on the podcast.
Thank you. Excited to be here.
So let's get straight to it. Sodium batteries. There's an awful lot of hype and excitement and investment going into sodium-based batteries. Could you just give our listeners a brief overview about the category of sodium batteries and why that's a special thing?
Yeah, no, it's a really good question. I would totally agree that there's a lot of hype, there's a lot of investment. Unfortunately, we're not quite seeing as much of that investment ourselves, but yeah, in terms of like an overview, there's several types of sodium-ion batteries. I think the most common and the one where we're seeing the most hype is kind of the twin of lithium-ion. As a twin myself, maybe it's more of a fraternal twin. There's definitely a lot of similarities, but there are some differences. But I think that's what's making it very exciting for people is the opportunity to have a ready-made replacement or drop-in alternative to the juggernaut that is lithium-ion. So sodium-ion batteries, the analog of lithium-ion, use very similar or the same processing equipment, but obviously have a lot of benefits, whether around sustainability, particularly for those of us looking for a more robust supply chain, a domestic supply chain outside of China. A lot of advantages around sodium-ion as well as on safety and other benefits. The other class, and where actually Adena Power is more focused, is in sort of higher temperature sodium batteries. So these would be akin to the sodium nickel chloride or Zebra battery, or the sodium sulfur battery developed by NGK. So there's really two types of families. I think the family that's getting the most interest and I think the most excitement and likely the most likely to compete at those high volumes with lithium-ion in the future would be the analog sodium-ion batteries. So looking forward really to talking about both and kind of talking through kind of some of the decisions we made with Adena in terms of why we looked at the specific technology we looked at, but definitely see lots of similarities and some of the benefits between these two.
Well, let's go to Adena now then to set the scene. So your company, Adena, can you give us the baseball card for Adena? How long you've been going? What do you do? How many employees? Capital raise? That kind of thing.
Yeah, so Adena Power, we've been going at this for a couple of years now. We spun out of a parent company called Nexeris that's been in the clean energy space, particularly in solid oxide fuel cells and electrolysis for over 30 years. So we were motivated several years ago to explore the energy storage space and really look at where we could take some of our core competencies in terms of solid oxide fuel cells and ceramic experience and look to see what opportunities there were in the battery space. So currently that we're a team of 6. We're relatively new. We're a startup, and we're looking for that initial seed investment at the moment.
And how long has Adena been going?
It's been a couple of years. So since 2022, end of 2022.
And now here's the layup, the question that I'm sure you find the easiest to answer, which is what's so wrong with lithium-ion batteries? Now, why do we need an alternative to lithium batteries in the first place? There's so many. It's a mature technology. You've got production lines churning out loads of these things. Why would we even consider an alternative for lithium-ion cells?
Yeah, it's a question I often consider late at night, being like, why? What is going to compete and what is going to be needed other than lithium-ion? I think one reason that motivated us with Adena Power. So I mentioned our parent company. We developed a lithium-ion safety monitor called Line Tamer, which gives the earliest indication of thermal runaway. And we commercialized that. It's now been distributed worldwide by Honeywell for both stationary and now the emerging EV market. And I think that really gave us an appreciation of the safety challenges with lithium-ion. I think there's been a lot of progress here over the last years in terms of improving the safety of lithium-ion. But I think from the most recent Moss Landing fire, right, there's still an inherent danger and safety concern around lithium-ion. You begin to look at the different AHJs that are looking at energy storage. I think you're based or taking the podcast here from Austin. I know Austin is an area where there's the AHJ there has concerns around lithium-ion batteries. You look at New York City or some of these large urban areas where it's very difficult now for the permitting for lithium-ion. So I think safety is a concern. I think the other appreciation is just how big a concern. And that's something over time we've really begun to understand more. As maybe it's not the inherent safety, but there's the cost implications from ensuring the permitting that's been a challenge. I think the other key piece I alluded to is that sustainability angle, particularly those here in the US and in the West are looking for more robust different supply chains. So it's what motivated us with Adena to look at developing a safer, more sustainable, and ultimately have a path to a lower cost energy storage solution. I think as we've seen here though with LFP pricing over the last couple of years, that cost value proposition is a difficult it's a difficult value proposition, and we need to be thinking and we need to be looking ahead. And I think there's a recent paper that came out just last month around kind of looking at how Soidum-ion, and again here's the lithium-ion analog, has with the materials bill of materials has the opportunity potentially into the next decade to be cost competitive with where lithium-ion is. So I think there's a lot of needs for alternatives to lithium-ion, and that's something we're wanting, that motivated us ultimately with Adena Power.
And now to go to the flip side then, how does a sodium-ion battery cell work? And what are the materials that are in of course, sodium, but what are the materials that are in a sodium-ion battery compared to other types of battery cell? And why are they better materials to use?
Gotcha. So maybe if we consider the sodium-ion analog of lithium-ion, and so in many ways very similar. You have anode cathode electrodes, and you have a separator. You typically will have a salt solvent electrolyte. In the case of sodium-ion, instead of graphite, you're likely using a hard carbon-based anode. I think that's really interesting. There's a lot of routes to make that hard carbon. Different approaches there that I think are very interesting, and from a circular economy perspective, have advantages over lithium-ion and graphite anode. I think on the cathode for sodium-ion, there's several types. There's the sodium layered oxide, so more, again, akin to maybe a traditional NMC type cathode for lithium-ion. There's the phosphate-based kind of polyionic materials, and then there's the kind of Prussian blue analog. So I think there's a range of different cathode chemistries that people are exploring for sodium-ion batteries. I think all of these, you look at the materials that are going into these cathode, and there's less critical materials than we see in a typical lithium-ion battery. I think that's one of the advantages. For Adena, I mentioned we're looking at the sodium metal halide-based chemistry, so a higher temperature operating battery. In this case, it's actually a solid-state based battery. So we use a sodium-conducting electrolyte, so a ceramic, a Nazicon ceramic membrane. This is, again, taking our core competency, our background in solid oxide fuel cell processing. We know how to make.
So there's no fluid, no pouch.
Exactly. It's a
solid state.
Yeah, it's a solid state battery with an iron. Well, we're using an iron salt based cathode chemistry. So typically people used a nickel-based cathode. What we saw when we started this was, in order to get to the cost that we're going to need, we need to substitute a lower cost material than nickel. So we use iron. So it's an iron salt based cathode, and it's formed in a discharge state. So the sodium that forms on our anode, which will be molten sodium at our temperature, forms during that first charging cycle.
Okay. And so what about Adena then? What's your, is it an intellectual property advantage that you guys have, or is it something else?
Yeah, I think what we took, and again, when we began this journey, really evaluated, okay, what are our core competencies? How do we find a technology that we can really leverage these competencies to build that defensible position, that IP advantage? So we have a lot of know-how, processing know-how in the manufacture of these ceramic membranes, and we have very vertically integrated. So we synthesize the powder and they integrate IP from the powder synthesis, the membrane, up into our cell design. The other thing we did, and I think it was probably one of the smartest thing we did, was we realized very early on that we don't know everything. We know very little. There's people that have been out there that have been working on these types of chemistries for a long time. And we partnered with them, in particular with researchers at Pacific Northwest National Lab up in Richland, Washington, who've really been working in this space of the sodium halide batteries for 10 plus years. They had IP around an iron-based cathode. So what we did was we worked with them. They've become really great collaborators for us, but we were able to secure an exclusive license from them to allow us to use or substitute iron instead of nickel within our cathode formulation. So we've been able to, I think, blend and marry our own IP and our own IP developed from our cell design and our materials know-how, kind of incorporate then the complementary IP from our partners.
And why does high temperature matter?
Mm-hmm. So I've got to be careful because I come from a solid oxide fuel cell background. So high temperature and ceramics background, I'm like, okay, this is 1,000 C plus.
Okay.
I would say more
higher temperature.
More warm temperature, I guess. So it's a really interesting kind of background. So the traditional sodium metal halide and sodium sulfur batteries typically operate 250 to 350 degrees C. And there's reasons for that, but one of them is they're based on a tubular cell design. They're very thick ceramic electrolyte. And what we did, and again, our cell design is based on a planar cell format. So what we did was took this thick tubular ceramic and we transformed our format into a planar, so with a very much thinner electrolyte thickness. That allows us to operate at a lower temperature. So we operate at a balmy 170 C, but that difference is enabling it in terms of it opens up our materials design freedom. So instead of having to use high cost glass ceramics, we can use polymer sealing approaches, which we see as an advantage. There's definitely, though, an argument there is an auxiliary heating needed for our batteries to get to temperature. So what is the benefit? And I think that's something we've had to educate people upon. I think operating at a higher temperature, what that does give us is a insensitivity to the ambient temperature. So unlike a lithium-ion battery that may be having to be temperature needs to be tightly controlled, because we're operating at a higher temperature, we're able to be more forgiving in terms of the ambient temperature. What that means is we don't need the HVAC systems, which are typically needed and often are the Achilles heel of these larger energy storage deployments. Indeed, when we've talked to one of the utilities we talked to, made the statement that going out to these large utility-sized energy storage deployments, often all you're seeing is row upon row of HVAC systems. So being able to simplify that, I believe, gives us an advantage at that system level.
And you and the team at Adena have partnered with some impressive institutions. So the Pacific Northwest National Laboratory, for example, also the US Army. Could you talk a little bit about your partnerships with those organizations and what that's done to your R&D roadmap?
Yeah, maybe I'll talk a little about the Army and our knowledge, also the Department of Energy. We've been really fortunate to have secured for our early development funding through Department of Energy and the Department of Defense, specifically through the Army and specifically through the SPIR, STTR programs. And they've been a really great non-dilutive funding source for us to kind of take our idea, our concept, and scale it beyond the lab into kind of these module demonstrations, which is where we currently are. So we've been incredibly fortunate for that funding. Really enabled us to advance the technology to where we currently are. As I mentioned before, the partnership with Pacific Northwest National Lab has really allowed us to accelerate our technical development. They, as I mentioned, they have years of experience with this type of chemistry, and so it's fantastic to be able to, if we see something odd or strange or we don't understand in our cell data, to be able to pick up the phone, or I guess more likely now, pick up the Teams call, and then just have someone on the other end of the line that typically will tell us, well, yeah, we encountered that 10 years ago. This is what's happening. This is how you can solve it. So it definitely shortens that development cycle. It's allowed us to focus, I think, less on the fundamental chemistry and understanding, and more on how do we take this and make it into a solution. And that's been really important. I think the other piece, one thing that really attracted us to this chemistry, is that it's proven. So you look at, this is the same fundamental chemistry that GE looked to develop with their Duraform battery. And as we were looking at different battery chemistries, what we kept coming back to was, well, the performance was excellent of this technology, and why didn't get the adoption that, based on the performance, we would understand. So we reached out, we seeked out as many people who worked on that technology at GE that we could find and we could talk to. Really kept asking the question, well, what happened? Why didn't get the adoption? We heard many things. We heard 2010 very different, and I agree, very different to now. And but we also learned of these two fatal flaws: one around that cylindrical cell design, and one around the use of nickel. So what our approach was, okay, we know fundamentally the chemistry works. There's data that shows the long lifetime, the durability, the cycle life, the calendar life. What can we do? What can we bring our technology, our experience, and our IP to address those fatal flaws? So that's where we redesigned it in a planar format, and we licensed the iron for the nickel.
And what does success look like for Adena? Maybe if you talk about the company and your milestones, and then I'd like to ask you about the wider sodium-ion community or category, what adoption looks like there. But firstly, for Adena, where are you guys at right now? What are you aiming to do in the next few years?
Yeah, so where we currently are is kind of demonstrating at the building block module side. So we've taken the technology from the lab out into kind of a module level, couple kilowatt hour type demonstration size. What that has given us confidence is around is kind of the stacking of our cells, the integration with our thermal and our battery management systems, I think positioned us to engage with larger demonstrations. So what we're working towards is those larger, more product intent demonstrations. And we're fortunate to have several utility partners that are very interested in evaluating the technology. So part of our roadmap is advancing that product readiness, so we can get to those demonstrations, really show the use case, still at a pre-pilot stage, but really integrating, whether it's integrating with a solar array to show kind of a solar clipping use case, or to really begin to show and validate kind of the techno-economic analysis we've done. That for us over the next year or two is the key milestones on the technical side. We're also looking, and I think for us is how the market matures in terms of how does our technology, our product roadmap align with the market roadmap. So we see the general landscape. We see as I said, the the juggernaut that is lithium-ion, and you can argue there's also the sodium-ion. There's a lot of shorter duration energy storage opportunities there, and I think it's going to be very hard for any new technology to compete in that space. So we are deliberately designing our cells, our technology, looking more for the longer duration space. So 10 hours plus, that intraday range. It's interesting. What we heard when we began the journey is lithium-ion will be, it's always going to be 4 hours or less. I think we've heard over the last year or two that duration keeps going up, 6, 8. We even heard from someone who said lithium-ion will take all storage up to 36 hours, and they were very nonchalant about that. So I think if that's the case, I think it's really difficult for other technologies to compete. But we do see a space where there is that opportunity for other emerging technologies, and where there's that need. So I think in terms of the sodium-ion battery space, you begin to see it probably as the most compelling, the most promising battery technology to compete with LFP here in the foreseeable future, because of the fact that it can leverage the 30 years of, it's so well aligned, it can leverage that 30 years experience that lithium-ion has. It can take advantage of all the cost reduction that's already been implemented. And I think there's that motivation, that desire to have a more decoupled, deconvoluted supply chain, and that will help drive it forward here in the US and elsewhere. So to me, I see sodium-ion, and again, this is the lithium-ion equivalent, being competitive with lithium-ion here beginning of 2030s. I think you're going to begin to get to cost competitive at that stage. I think both will coexist. They will be, if we go back to that twin analogy, that they will be able to find a way to coexist together. And that's where I kind of see the market adoption.
And what's the trade-off with sodium-based cells then? Is it an energy density? For example, if you think about NMC versus LFP, even if you go and buy a Tesla today, the performance Teslas use NMC and the standard ones use LFP, and you can see why, because there is a trade-off on current and performance. So, how are you thinking about the trade-off between sodium-ion and other types of technologies, and how does that affect the way you develop these kind of cells?
Yeah, so I would say for sodium-ion, because sodium's heavier than lithium, all being equal, your energy density will be lower. So your gravimetric energy density will be lower. So where those applications where gravimetric energy density is not as important, so I think definitely in the stationary energy storage space, sodium-ion could be very competitive. I think sodium-ion, the energy density is close enough, particularly to LFP. And I think with the system advancements, the cell enhancements, you can get close enough that sodium-ion is a viable path for the EV space too, which I don't think other emerging battery technologies are, which I think is what gives it the key, because it can get to the scale in order to be able to be competitive. Because ultimately, I see that the stationary energy storage market has really benefited from the market pool that EVs have created over the last 10 years. And I think the question that we posed ourselves was, is the adoption of EVs, or the ramp up of EV adoption, does that create different dynamics in the next 10 years? Is there a restriction in terms of the availability of lithium-ion that gives opportunity for these other emerging technologies? I think if you begin to see sodium-ion emerge, part of that is because of this the scarcity of lithium-ion. Although with 40 new battery facilities being built here in the US, there's like growth in demand. I think, and one way of thinking about it is, you look at the EV versus the stationary market, and the EV space needs energy density and cost, but energy density is critical. So it will likely continue with a lithium-based technology, battery chemistry. And I think for the stationary side, cost is critical. It needs to be low cost and it can give up energy density. So I think that's where you're going to begin to see maybe the sodium-ion type batteries and other technologies as gaining market share.
Interesting. And what about your projections for, where do you think the sodium-ion battery cell technology is going to get to in the next few years? What are the milestones, and how does this market shake out?
I think it's a good question. Right? So I think sodium-ion will continue on a curve that follows very similar to lithium-ion. I think one of the questions is, how do people convert a lithium-ion battery processing line to sodium-ion? Is there a motivation for that, and what's driving that? One of the reasons with Adena we wanted to try and avoid a traditional battery processing approach is our concern around how do we, as a small startup, secure that processing equipment as we look to scale. So by using industrial processes, but not those associated with traditional battery manufacturing, our belief is that we can avoid any constraints around equipment. So we're looking for more kind of the traditional ceramic processing capital equipment, whether it's furnacing, those casting, those types of ceramic processing equipment versus some of the battery manufacturing. So I think in many ways, what will need to motivate the sodium-ion space will be a shift in terms of supply chain. I think there's going to need to be a greater driver, a greater motivator towards the need for robust domestic supply chain. So I think in many ways, the journey that sodium-ion will go on will be dictated by what happens here in the next 5 years in terms of geopolitical factors that could shock the system.
Okay, so now this is your chance to announce anything or to plug or to sell. So is there anything you'd like to plug to our listeners who are generally energy folks?
Mm-hmm. So I would say a couple of things. We've mentioned with Adena, we're continuing on our journey. It's a long journey we see from where we are. We are focused on continuing to secure that funding to continue to develop the technology. Really fortunate we have engaged stakeholders and partners who are helping us in that journey, but we're always looking for more people to engage with, more people to learn from, more potential customers to understand the market of. So that's definitely one area that we're always very interested to talk to people. I would say from the other side and from the energy space more generally, putting on my kind of Nexaris parent company hat, we're positioned as a solution provider and kind of technology agnostic at the moment. So we're always interested in hearing from customers, people in the energy space, in the climate energy space, who are looking to solve, I think like Adena, and we are trying to solve these challenging climate problems, particularly who have challenges around the materials and testing area that are looking for partners, because we're always looking for those customers to engage with. So that's and that's across the energy spectrum, from energy storage to electrolysis, fuel cells, catalysis. We will operate in that broad space.
And now for my favorite question, which is, what is your contrarian view? So what is your belief that you think not a lot of other people believe?
I think you look at the scale, right, of this energy transition and what we are looking to try and achieve as a society here in the next, if you say we want to be net zero by 2050. So the pace of a transition, which is unlike any we've really attempted in the past. I think one thing is there's not really any experts on the energy transition, because I don't think we've never done this before. So I think one sense is that we all have to be humble. We all have to have grace for each other, and we have to understand that there's probably going to be a lot more false starts, a lot more errors, a lot more technologies that don't make it, that a lot more money is spent, perceived wasted, but that's just going to be required in order for us to get where I think ultimately we all want to get to, and have an equitable energy transition that benefits society. So I think that's one thing. I think from a technology space, and you look at the amount of storage that needs to be deployed, whether batteries will be the enable us to get all the way, I doubt it. I think there needs to be all of the above, in particular as we look out to longer duration. And I think maybe the contrarian view I have is that I see pumped hydro, particularly nearshore pumped hydro, as probably becoming more important. I think there's opportunities around the U and looking at the US. There's locations here where you can begin to install that level of pumped hydro, which could give you the energy storage that we're going to require, right? I think for those longer durations, for when we're up to 80% renewable penetration and above, where we're going to be heavily dependent on storage to ride out those multi-day weather events, we're going to need more storage, I think, than what batteries or electrochemical storage will be able to provide. So I think the need for long-term, large-scale energy storage and government kind of intervention to enable that is going to be required.
So you reckon that the demand for energy storage systems on the power grid will exceed, will hit the limit of what supply can supply?
Mm-hmm. I think so. I think what we're going to have to, I think it's going to be interesting, right? As solar begins to increase, so our electrical generation mix becomes solar, essentially. I think that's the way we're evolving. You begin to see daytime, we're going to shift from a summer day peak to likely a winter kind of night is when we're going to need to have kind of the storage, particularly as we begin to electrify all our homes, electrify everything. I think we're going to shift for when we actually need electricity, and I do see us kind of moving more to a winter peaking type position, and you begin to concern around, particularly here, maybe not in Texas, but up here in Ohio and at these more northern latitudes. How do we support the winter demand that's going to be needed again as we shift to more electric heating, EVs, like with diminished solar during those winter months, and how do we support that? So there's going to be probably an even greater need for storage than we're aware of, because ultimately we need storage 24/7, 365, or we need that reliable electricity. And I think that's going to be the hardest challenge for us, is that how do we preserve or maintain a reliable electricity grid with that high renewable mix in those months of winter where solar generation is lower than in summer.
And you think the answer is hydro, pumped hydro?
I think to get to the scale that we're going to need, we need to be thinking, I think it's orders of magnitude more than even we comprehend, right? So ultimately, if we need to ride out a multi-day weather event, we need hours of storage reserves. And I think you look at even what we're adding currently with even the battery storage we're deploying in the last few years, it's minutes of additional storage based on our current max usage. And how do we how do we get to have those and it's reserves as well, which I think is interesting. It's not assets that you're going to be able to deploy and monetize for shorter duration. I think how do we keep these storage reserves and how do we incentivize that? And I think that's a real challenge.
Okay. Well, Neil, I want to say a massive thank you for joining us on the podcast and telling us all about the work you're doing in the sodium-ion sphere. If you listen to this podcast, want to find out more, we'll put a link in the show notes. And as ever, if you like Transmission and you want to get updates when new episodes come out, do hit like and subscribe. It really helps us increase our reach and helps more people find what we're up to. Thank you very much, Neil.
Great. Thank you very much. I really enjoyed it.